I think we should go ahead and get started. Welcome everybody to Morning Fuel. We're real excited to have our guests from Baker Hughes today. As usual, we're going to, your cameras will be turned off, and the way to ask questions is through the chat. And we look forward to lots of questions. I'm going to hand it over now to Brooke Simmons to introduce our guests.
Thank you, Mr. Chairman. Well, folks, I'm really happy that we are having this discussion today. This is the first of several technology discussions I think we're going to be having as we move throughout the year. It's going to be really incumbent upon us, I think, as an industry, regardless of sector, to understand where the puck is going and how technology in this next phase of our evolution is going to play a leading role. And it doesn't matter whether you're talking about the so-called energy transition or carbon optimization, or just how to do things more efficiently to make more money. All of this technology conversation is part of that. And I'm excited to have Maki Ikeda with us today. Maki and I have been talking for a number of months about this, and I'm really excited to kick it off. Let me tell you a little bit about Maki. Maki is currently the director of the Energy Innovation Center for Baker Hughes, located in Oklahoma City, just up the road. Her career in oil and gas took her through several different roles, including working in offshore and onshore field operations, leading reservoir engineering teams, driving technology solution development, new ventures, business strategy. In her current role, she's leveraging traditional oil and gas expertise with technology advancement in the digital and energy transition spaces to drive disruptive innovation. And we have an industry that is full of wonderful disruptors. So Maki, thanks for being here today. Please introduce your team, and we're going to let you drive for a while.
Yeah, thank you, Brooke, and thank you for the Petroleum Alliance for having us today. Thank you, everyone, for attending today. Yes, I have together with me two of my team members, Xiaoxin Ji, who is our computer vision team lead, and Sam Tanner, who's an edge analytics engineer. Both are striving to apply and adapt new technology innovation for our customers. So they'll describe a little more, what they do, how they work with customers, and what technology it's all about. When probably you may not know what a computer vision engineer is versus an edge analytics engineer is. So we'll cover a little bit of that. And really, this is more the start of a conversation, as Brooke said, rather than this is it for the 1 hour. We really hope this is, getting you think about what could be, or what could your business look like, or how can your operations be improved in the future, or as things are evolving, both from a regulatory perspective as well as a technological perspective. So I'll cover a little bit of our center and what it does, and then I'll let Xiaoxin and Sam talk about two specific areas they're focusing on with our customers. Great. So if you go to the next slide, I'd like to start with where we're at as a company. So Baker Hughes, similarly to many companies, has recently gone through a series of changes. And we have been part, as you know, part of GE and then moved 2 years ago through a separation. So now we're separating from GE, and we basically have grown our own identity and vision. And that's has been a really positive, transformative evolution, rethinking our role in the energy industry and beyond. So what you see here at the top is our mission today. We take energy forward, making it safer, cleaner, and more efficient for people and the planet. So that really kind of is broader than just a traditional oil and gas industry we've covered in the past, maybe, or as you have been dealing with Baker Hughes. So if you go to the next slide, we have brought together 4 different businesses. As you see on the left side, oilfield services and oilfield equipment, which is very focused on oil and gas business. Oilfield equipment is more the subsea and offshore business, and then turbo machinery and process solutions, which is all the services and offering around compression, turbines, as well as the LNG services. Our digital solutions business has a lot of high-end sensors and control systems that are applied not just in the oil and gas industry, but also in the aviation, in the automobile industry, as well as telecommunication. So you see, we're really kind of expanding beyond oil and gas and looking at other industries. And also we are, energy transition, and I'll talk a little more about what it is, but is really driving our activities. We've had a stand. We've publicly announced that we're going to be net zero by 2050. That was 2 years ago. And every day we're looking at, how to decarbonize our company as well as our customers. And how we do that is a little bit with the disruptors that you're seeing at the bottom. The accelerators are related to digital. So automation, multi-physics simulations, machine learning, augmented reality, and new materials. On the right, you see what has happened last year, some of the key metrics that you might find interesting. And I'll just highlight, for example, that we provide a lot of monitoring system for wind turbines in the wind industry. Also, we sell about 800,000 plus sensors annually through the digital solution businesses. And also in terms of pipeline, like 42 million plus feet of pipeline that we monitor. If we go to next slide. Yeah, so just refocusing now on the Energy Innovation Center. It's one of Baker's leading research and development facilities in the energy and industrial innovation. Our mission is to really be at the forefront in providing thought leadership for a company. And we're constantly rethinking how we work, how our customers work, to see how we can, make operations faster, more efficient, more productive, cheaper, whatever the need is. And our strength is to look at, new concepts, to test them, and develop them, while really the commercialization part is done through the businesses. And we're a little bit of a window to the outside to look at what are the technological advancements outside that we can bring back home, and leverage them within our businesses. And just to note, we're one of the 3 enterprise level technology centers. There's the 2 others are additive manufacturing, so 3D printing, in other words. And the other one is more on the cloud infrastructure and digital side of things. And they're located in Houston and India, respectively. And we work hand in hand in most of our projects just to leverage both our capabilities. And if you go to next slide, this is the most recent update to our center. And most of you probably are aware of it, but we've basically signed a technology partnership agreement with Oklahoma State University. And that was a really exciting, next step. We've donated our building to OSU, and through that, we have opened our space for a broader collaboration, not just OSU, but also, that whole area is developing into that large innovation hub. And we have, other partners that want to also, come into the space and collaborate and look at, technology projects within oil and gas, but also, we have other partners that are coming in the automobile industry or aerospace. Our lab welcomes external companies now to use it, and we are also looking forward to return to the building for more interactive engagements. If you go to next slide, just at a glance for our center, we are a very diverse set of engineers. We have about 60 plus engineers with a mix of background, as you see, mechanical engineering, chemical engineers, digital, which is computer science, and then more traditional, geoscience, as well as petroleum engineers. And I would say most people have, either on the job or on their own, learned more about digital, whether it's data science, machine learning, or data engineering. And really, most of our engineers have that double profile around, fundamental science as well as now a little more digital, which is really our strength because we don't compare ourselves to, the Microsoft or Google, but really apply digital within, physics-based types of operation. And we know how mechanically things work. And now we're trying to ingest some of the new technologies or techniques that are used outside. If you click one more, this is a little bit of what we have in the lab. Very traditional equipment like test wells, flow loops, core scanning equipment. But what I would say we use now a lot more are the electronics lab as well as our scanners. And we traditionally used to scan, rocks and core samples. But now we've started to scan, other parts, like for example, parts and other parts, so that and we use it to inspect them more from a manufacturing standpoint. How do you assess whether there are defects and if there are defects, then you kind of bring it back to manufacturing. And this is more of the work we're doing with the automobile industry on inspections. So we're kind of leveraging equipment that we traditionally used for oil and gas, and now looking at, hey, where else can we use it? And that has been a very interesting, technology transfer in a way that we have worked on. If you go to next slide. So this is a bit of what we do and how we work, especially with the external partners. Obviously, as a research and development center, we have strong collaboration with universities to really accelerate some of the lower technology readiness concepts. And we don't do, usually when it's very early stage and pure research, we don't do it internally. We let universities do it for us or with us. A second aspect where we are partnering outside with both universities and corporations and private companies is on the external funding side of things. So there's a lot of funding out there by the DOE or other entities that are providing support to accelerate understanding of new technologies in the oil and gas sector, but also more broadly in the energy sector. And we've learned, to really leverage that with our partners to look at new areas, new markets, and new applications, and basically test them through this mechanism. So just one highlighted here was, for example, applications for hydrogen that we just submitted last month, but also, regionally, we're working with OSU and a separate one with OU on like energy management and waste heat recovery. The other aspect is tech development. That is really most of what we do is internal technology development for our businesses or for customers. And then last but not least, we do a lot of partnership and tech scouting, because we know a lot of people are doing things better than we do. For example, Microsoft or Google, they are, they know how to use data, cloud infrastructure. So we really leverage them instead of building our own infrastructure. So Google is a strong partner as well as Microsoft, and you also know probably that C3 is one of a strong partner as well. ANSYS is another one, more from a modeling side and engineering side. You go to the next slide. And now areas of interest, as we mentioned earlier, digital and energy transition is some of our key themes that we're interested in. And I just want to pause and maybe explain a little bit what we mean by energy transition, because it means a lot of different things depending on who we talk to. And really, I talk about it through more decarbonization rather than energy transition. So decarbonization is really reflected through different areas. First, you kind of want to know what you need to decarbonize or how much you're emitting in a way. So that's kind of the left corner in terms of emission management. And depending on regulations, you might not need to monitor it, but you might be interested in knowing how much you are emitting just because of regulatory reporting purposes, or also just because of your interest in reducing your emissions. For example, compression is emitting a lot, and that's one of the large efforts that we're looking at, like how you can reduce emission. And then that leads me to the energy efficiency side of things, where first thing is, can you make your operations more efficient rather than completely changing. So just looking at asset efficiency, meaning optimization of how they operate. So whether you understand the best operating range, or you make downtime, you reduce downtime, that can be areas that you would look out. And then energy efficiency is more like, okay, if you are emitting, what can you do with it? So waste heat recovery, for example, can you use that heat and transform it somewhere else, to something else? And then looking at sustainable infrastructure is when you think about, okay, well, I don't want to just improve the efficiency. I think a better option would be to replace it with something else that is less carbon intense. Or when you're starting a new project or new infrastructure, you would look at a variety of options. So electrification is something that a lot of our customers looking at as a first, not looking at diesel or gas powered. And then a little more going more modular, reusable facilities, also leveraging low carbon materials like non-metallic, and looking at advanced technologies for manufacturing, like I mentioned earlier, additive manufacturing or 3D printing, that really reduce the amount of material you're using just to build one part. We were able to reduce 60% of the mass just by switching from traditional manufacturing to additive manufacturing. So those types of things really help when we think about being more efficient in how we use material and how we use energy. And last but not least is probably what everyone knows about energy transition is carbon capture, hydrogen, geothermal, and all that. So that was a bit of a picture of what we touch and how we touch it differently depending on basically customer needs, right? Not everyone is going to hydrogen. A lot of people are still around how do we make our assets more efficient, how we utilize some of our waste. So I would say a lot of our work is done with customer on the energy efficiency side of things. So that wrap up my section really, and then so I'll pass on to Xiaoxin, and she'll cover the computer vision space.
Okay, thank you, Marky, for the great introduction of EIC and Baker. So what I would like to cover today is really want to have an overview of how we are applying AI and computer vision technologies in oil and gas industries, also including some other industries. Hopefully that reflects how we are transforming ourselves, like through the digital transformation journey into an energy technology company. So if we go to the next slide, I would like to start with a brief introduction of the advanced analytics team at EIC. So we are a team of 28 members focusing on AI and data science, but is also actively supporting other domains within enterprise technology, like edge computing, multi-physics simulations, and additive manufacturing. So more than half the team are based off Oklahoma City, focusing on machine learning, AI technologies. And as Marky mentioned previously, we have a mixed background of domain knowledge on gas industry, as well as some data science technologies which help us to find valuable use cases in this industry. So the rest of the team spreads across North America and India, focusing on data engineering and physics-based modeling. I want to say that the unique and diverse skill set really covers the whole life cycle of the analytics development, all the way from the data engineering, data management, to the core analytics development, all the way to the deployment, which scale up the technologies to productization. So the team has been working on a very wide varieties of applications, include white space innovations and product-oriented applications, right? So here, our main focus areas currently are on the intelligent inspections, also supporting additive digital thread, as well as some field service digitalization. So if you could go to the next slide. So before I dive into like specific use cases, right, I want to give a high-level overview of what computer vision is and how we can potentially apply it to different use cases. So what is computer vision? So it is a kind of like hot and buzzwords. We've heard a lot from the media. So what it really does is it's actually developing technologies that help the computer to see and understand the content of digital images. So it seems so trivial for us as human beings because it's our natural ability to see something. Oftentimes we fail to appreciate the challenges that the computer is facing. Because so when you are looking at this video, your eyes and your brains work seamlessly such that you can subconsciously see and track the objects of interest, even if you are just glancing through it. But to computers, this task is never easy because all it sees is not just pictures, arrays of numerical values, which is always struggles to make sense of. So long story short, scientists and researchers have been working on this problem for decades, but it's only until recently that the computer vision models actually getting close to the human level performances. And what you are seeing here is actually the real-time output from a computer vision model that people use on autonomous driving, which can identify different objects and track it with pretty high accuracies. And again, that's running in real time. So it's achieved the human level performance in both speed and detection accuracy. So in the interest of time, I'm not going to walk through any technical details or breakthroughs behind this thing, but today I really want to cover a series of applications where we apply the computer vision technologies to different use cases. Hopefully that offers a more concrete demonstration of the team capabilities, but more importantly, help resonate some good ideas for future applications. So if we go to the next slide, this is actually a big picture of how we are applying computer vision technologies to some oil field applications. We have worked on the projects we have been working on. So we know that AI has been a game changer for a lot of industries, for countless applications, and also it is making its way into the oil and gas and energy segments too. So listed here is by no means a complete list, but a few samples where we apply the computer vision technologies to help drive operational efficiencies, cost out, as well as to enhance safety. So I'll start probably with the top left, which we have a ground monitoring system, which is really a truck that has been retrofitted with a couple of sensors and cameras, which helps to monitor the real-time road conditions, emission levels, as well as to capture some unique market intelligence while we have the service trucks travel in the oil field. We also deploy some digital, or we call mobile apps, that we use to help accelerate the data entries to digitization or doing automatic inspection of equipment on the field. We also have a use case where we have cameras that is mounted on the skid, deployed on the remote site. Without interconnection, it can run some intelligent analytics for site surveillance and personnel safety monitoring without connecting to the internet, and generate some very valuable insights at the edge for the operators to monitor site safety as well as to do some event logging. Last but not least is on the office or shop level, we actually have some use cases where we deploy the mixed reality technologies into some very innovative applications that help to promote collaborative design or help promote remote training. There are also use cases, as Marky mentioned, we use these technologies to perform intelligent inspections to improve the efficiency and outcomes of inspecting different equipment. Hopefully this gives a picture what I'm going to cover today. So now I'm probably to take a little bit deeper dive into different themes. And the first one I really want to cover is the intelligent inspections. So we know that some hardwares of applying computer vision models includes autonomous driving, machine vision, and intelligent inspection is probably one of the largest market that is applying these technologies across different industries. So we have Baker Hughes has a business called Waygate Technologies, which is under our digital solution tier 1 businesses that makes or offers a very wide variety of sensing and measurement products, including CT machines, ultrasound sensors, borescopes, and many other sensors. So what I've listed here is actually a collaboration we have with the Waygate Technology businesses to develop the next generation inspection solutions that use AI or computer vision technologies to automate and improve the inspection process. We know that the sensors actually provide different types of insights into the objects to be inspected, but they are suffering from either image quality, the size of the defect, or they are large volume data to be inspected. So currently, they're still done in a manual way, but it takes about probably an hour for an experienced inspector to go over just one 3D volume file, and that still doesn't guarantee 100% detection. And that's exactly the reason why we are trying to bring the AI technologies to accelerate the process, but also improve the accuracy, consistency, and generalizability of the inspection process. And so I think this technology, there are 3 projects I've listed here, which use CT machine or X-rays to inspect lithium-ion batteries in consumer electronics, in electric vehicle batteries, as well as casting parts of automotive aviation parts, right? So this actually 2 out of the 3 technologies I have listed here has already been transferred or is currently being commercialized by the Waygate Technologies that is going to be released to our key accounts later this year. And this is a key enablers for our digital transformation that offers not only hardware, but also solution and service. But also, more importantly, brings help improve the efficiency of the inspections to the customers through reduced total takt time and enhanced throughput and inspection outcomes. So next page, actually, we have more examples of how we are applying the technologies to different use cases. So in addition to the CT imaging, we also have deployed the technologies to a borescope, which is a handheld device we use to inspect gas turbines. So this is the first edge analytics we deploy in the market that not only improve the inspection outcomes, but more importantly, reduce the time and the training and specialization needed to onboard new inspection technicians. As you can see, it's kind of like digitization of the experience that would put into the intelligence of the product. So on the additive manufacturing side, so we have an additive manufacturing tech center based off Houston, which prints thousands of parts for different industries, including oil and gas, drill bits, valves, and many other equipment. One challenge they are having is really how do we ensure the QE/QC during the printing process so we can detect and correct the defects early in the process. And that's why we have a camera and have automatic defect recognition software developed for this process that we can not just saving time and cost by early detection of defects, but also feed that valuable insights into the process that we can improve the printing in the future. The last application here on this page, I think is more related to the oil field applications. So we actually have working with our drilling services to develop a mobile app called Instagrade. So our field technicians actually have a mobile app and use his cameras to take a picture of the drill bits on the field when he's doing servicing. And that by having a computer vision model running on his or her cell phone, this app is able to detect each cutter of the drill bits and automatically assign a bit downgrade that helps to enable fast, consistent, but more repeatable bit grading. And we also have this app that can doing automatic text recognition, which helps accelerate the digital entry of the data entry of the bits record data, as well as use some insights we get from the apps feeding into a bigger database that helps to improve manufacturing and design process of the drill bits in the future. So that is what we have on the intelligent inspection side. So the next page actually covers the use cases where we deploy the computer vision technologies to for ground or operational monitoring on the oil field. So as I briefly mentioned in the previous slide, so we have a project called SafeSite that we use cameras and some edge computing, which means you can run analytics locally without connecting to the internet, which Sam's going to cover in a few slides. But here we use the technologies to validate the field tickets, to provide some event logging that helps to monitor the site safety and personnel safety, as well as to improve the operational efficiencies through the event logging and the operations activity monitoring. On a similar vein, we apply the same technology stack, but mounted on the truck. So we have a lot of service trucks running in the field, so they are perfect candidates for passive data collection. And by using sensors and different cameras, we're able to monitor the road conditions as well as emission level in real time, covering a very good temporal and spatial resolution that help us to enhance our own HSE, but also for the operators, as well as a first screening of emission monitoring on the field. It also offers a very unique insights of oil field services activities by monitoring, for example, how many rigs are up there, how many sites are being constructed or converted from drilling to production. So the last topic I want to cover on the next page is augmented reality and mixed reality. This is actually a very cool technologies which you may already experience with gaming, like playing with HoloLens and some other equipment, right? So here we actually extend the application of the technologies to both oil fields as well as medical applications. So on the left is a demo. We actually demoed to our boards a few years back, which we applied the augmented reality technologies on different devices, on iPhones, iPad, which actually on the left is a picture showing how we are overlaying a 3D CAD model of a wellhead on an actual wellhead. And by connecting to the CAD system, we're also able to visualize the sensor data in real time, which not only promotes like the better visualization of data, but also helps promote the remote collaborative design through different locations and offering a virtual training opportunities to improve the efficiency while reducing the carbon footprint. And on the right is a medical applications. We actually use this technology, first of all, dynamically tracks an object and overlays the full detail CT or MRI data on the patients, which actually helps the doctors to improve the diagnostic results and enhance the surgery process. And that has been actually validated as promising technologies by a lot of surgeons in the Oklahoma areas. And we see this as like and applications, we extended our capabilities across industries and create impacts across different vertical segments. So with that, I'll probably conclude my presentation on the computer vision side. I'll probably pause for a few minutes to see if there's any questions. And otherwise, I'm happy to answer any questions offline after this presentation.
Maki, we've had a few questions come through there. Do you want to hit a couple of those questions, Maki, before we transition to Sam?
Yes, and Xiaoxin, I guess there were a few questions uh, around the bit grading, whether it was, applicable to non-baker and whether you need a before and after.
Mm-hmm. Oh, that's a great question, right? So when our field technicians use this on the field, right, it's not just Baker Hughes drill bits. It's drill bits from all operators and our customers, right? So by like working with the customers, we're able to use the app, the mobile app, to grade like any types of bit grades. But given that we have this in our database, but as we are grading more, we are building a larger and larger database. Then that offers actually a very flexibility when we are working either with our own drill bits as well as the operators.
So one of the things you were talking about is the wear measurements that you're going to be gathering.
Mm-hmm.
One of the things that it seems to me, and we did this with submersible pumps, the curves for those particular pumps, what we did is they publish like what the curve is. So they'll publish what the particular bit performance is supposed to look like. But we were testing new pumps before, so we had a curve of that specific pump. So when we went out and it started performing differently than that, we were measuring against not a manufacturer suggested performance, but the actual performance of that particular pump, or in this case, that particular bit. So it seems like you could get a imprint the parameters of what the bit that you put out there is within tolerances of what your manufacturer performance would be, but you would have like a picture of what that particular bit would do, and you could always compare that against this data that you're collecting. Is that one of the things you guys are working on?
Yeah, I think that's actually falls in the category of using a larger metadata, right, associated with the drill bit data itself to get more insights, right? I think that's eventually the big picture we are going to get there, actually using metadata for different purposes. I think what you mentioned here is definitely a very good example of how we are applying that.
So the curves that so the performance parameters that you're developing as you're manufacturing, it's better. It represents a larger population of the bits that you're producing, and so it is indicative of what you expect as performance.
Right. And also not only that the equipment is working with and the geographic information, like the field, like what field is drilling, right? That also provides some insights on the whole process.
And it's validating with the actual data, right? Whatever model you might have that copies the manufacturing specs, as you get real data, you would actually adjust the model, and that's really what the learning part is, where the model learns based on the active data, so that it applies more and more to that specific environment.
So basically, it just keeps improving the performance specs or parameters to where they're real life, real time, and tested against what you actually. So if you go out and a bit does not run, but 63% of the time before it fails that you were anticipating, then that goes into the mix, right?
Yeah, so actually what you're talking about is really like the where we want to go as the vision is how do you also embed next the manufacturing and engineering, how do you modify the bit so that it performs better the next time, right? And the challenge is do you want a more generic bit that can cover a different range of environments, or do you want that specific? And I think for unconventional US, you have very similar environments, so that's very applicable, so that you basically, and that's what we're doing, right? You adjust the bit engineering that it performs better in the.
So one of the questions is what's driving, what drives the technological changes or things we want to look at, and I've got to think it's in the oil and gas business, and for our constituents, it's got to be from the field. We need to learn how to do this better or that better. So how do the ideas come? And a couple of them, I'm asking a couple of questions. How does the ideas come to you to work on? And the second question is how do we get to know what things you're working on, so we're not recreating the wheel, and what access would a layman have to that kind of information, or get to be involved in it.
And Xiaoxing, I think Maki's computer may be frozen, so feel free to jump
Yes.
in.
Yes, I think I can definitely help answer the first questions, right? So how do we look for like the best use cases to apply the technologies? I think that is one actually the biggest challenges we are having, especially applying the disruptive digital technologies, right? So sometimes it's like looking like hammer looking for a nail, but I think what makes more sense is actually working with the users and the customers, really finding the valuable use cases that matters to their applications, not definitely applying those cool technologies, right? There is also a cultural change we need to go through together. How do we make sure like we are stay tuned to the technologies, and how we make sure we see the values that the technologies can bring to the field? I think there's definitely a teamwork between us.
Could you tell us about Edge and tell us a little bit about that technology and how that would help us? You know, most of the questions you're going to see that are running through here have to do with collecting data on wells, so we can for a variety of purposes. One would be managing our the wells by exception, more than going to every well every day, and some, you know, as practices.
Yeah, I think that's definitely a great segue into what Sam Tanner is going to talk about next on our edge computing. So
the SAMs, we have two SAMs.
Yeah.
Sam, you want to tee it up, Sam, and take it away?
Yes.
Okay, sure. Yeah. Well, I'm going to be speaking on edge computing today. My name is Sam, not to be confused with the other good-looking Sam on the call. So I'm very glad that people are asking questions about this. I hope I can address them, and please, if there's any more questions, I'd be happy to go in further detail. So my name is Sam Tanner. I work at the Energy Innovation Center that Xiaoxing and Maki have both discussed already. My background is in electrical and computer engineering. I've been working with Baker Hughes for the last 3 years on an edge computing platform. So I'm going to talk about that and how we've applied that with success in the oil field. Before I jump in, I'm not trying to hide this. Before I jump in, I want to take a little bit of a step back to describe what edge computing is for those that are not familiar. So over the past years, we've heard more and more about cloud computing, which is essentially taking data gathered by sensors in the real world, sensors and computers in the real world, and sending that data to a large central server that we call the cloud. So that's any data in the world comes to this central location, and in the cloud, these servers, you have just immense computing power. You have almost unlimited storage, and you can save this data and process this data and run machine learning models on this data with just massive resources that you've got to do that. It does have limitations, however, and many of these limitations are very highlighted in our industry. Namely that a lot of our locations don't have connectivity to the cloud, and if they do, it's inconsistent. It's not very good connection, so it's going to take forever to send the data back to the cloud, and then even longer to get, once we run applications on that data and make decisions based on that data, it takes even longer to get the decisions back to our equipment. So edge computing is essentially taking a small industrial hardened computer and putting that computer, connecting it to the cloud, but putting the computer right next to our customer's equipment in the field. So now you're gathering data from sensors and you're using that data locally. That reduces the cost to send data back and forth because you're using what you need right there, and you can send summaries back up to the cloud to review later or to store for longer term if you need. Importantly, if you're trying to, say, send a better injection rate to a compressor on a gas lift application, the compressor needs to know that pretty quick. It doesn't want to rely on waiting for the data to get sent to the cloud and the processing to happen in the cloud and then get sent back. So if your computer's right next to your compressor, that latency is reduced drastically. So that's what the edge is. When we say edge computing, we're talking about a physical place. We're talking about putting a computer next to your equipment, connecting that computer to the cloud so you can use the benefits of cloud computing, but you don't have to rely on them. It's not your only source. I think I've covered this, but basically it allows us to operate in places where you don't have very good data communication. It drastically reduces the cost of sending your data to the cloud, drastically reduces the time from gathering the data to getting an insight out of it to your equipment. And it's also a very inexpensive way of incorporating existing sensors and existing controllers into this digital scheme where you can make better decisions, you can use computing power, but you don't have to wire everything directly to get the sensors to the cloud. So this diagram on the right here, very high level shows. We've got our location with our controllers and our SCADA systems. We connect an edge device, a small industrial computer to them, and then we allow that small industrial computer to talk to the cloud, which is just a large collection of servers. So Baker Hughes, this is kind of how we've broken this down. This is the architecture we have. We take a small industrial computer and put it next to the controller. That allows us to run analytics in the field. Think like applications on your phone. We develop these analytics as independent applications, and we can manage them remotely. So if we've got a fleet of 100 different edge devices or 1,000 different edge devices out in the field, we can see all of these edge devices on a website remotely. We can see what analytics they're running, if they're running well, if they need to be updated. An important aspect of this is cybersecurity. So we've developed an operating system that's locked down. It's based on Linux, if you've heard of Linux. Android is also based on Linux. A lot of the world's computing power is based on Linux. So we've taken a version of Linux, we've locked it down to make it cyber secure. We encrypt all of the communications to make it so hackers can't steal the data back as it's being sent back and forth from the cloud to the edge device. And we have enabled the edge device, the small industrial computer, with Modbus connectivity. We also have OPC UA, but we found Modbus is one of the most common protocols. So at the bottom, there's a diagram of how this works. You take your existing controller, your existing sensors, you plug it into this small industrial PC, industrial computer, with our edge platform on it. It's got a secure operating system. It's got these different applications. We call them containers. That's another term that we use. And a few important aspects of what's running on the actual industrialized PC, the hardware, the edge hardware. There's a technician console to interact with the device locally, because sometimes it's nice to do things on the cloud, but sometimes you're at site and you want to see what's happening. We have a database available on the edge device. Obviously, it's a very small industrial computer. You can't store things forever, but you can store quite a bit of data on there over time. And you, again, summarize your data, your important long-term data, and send it to the cloud for longer storage. And then we've got a cell connectivity. So that's this line here that connects this edge computer to our cloud. That's where we can, the cloud is where we have the user interface, the web page to view all of the different devices, to send new analytics or apps, to update those analytics, to make sure that the operating system is updated and cyber secure. And that's also where we could store data long-term and put more user interfaces per each application. So if our customer has, again, to mention the gas lift optimization, they're going to want to see exactly what decisions our computer is making and how that's improving their production. That data can be sent to the cloud to be reviewed remotely. On the right-hand side, this is what an actual installation looks like. So we've got a reciprocating compressor. It's got a control cabinet on it. If we open up that control cabinet, you can see the two different pieces of hardware that we've installed to enable this edge computing. We've got the edge device right here. This is like a 5x5x3 little computer, and this is bigger than they have to be always, because this is a class 1 div 2 environment. Because of the area it's in, it needs to be a little more hardened and secured. With that, this one doesn't have an integrated cell router like your cell phone does. So we have to put two pieces of hardware in there. Some applications just require the edge device itself and have an integrated cell router. So every application that we've done this on so far, there has been room in an existing cabinet for us to fit these very small computers in, just to emphasize how simple this can be. Here's a diagram of a well pad. I've circled here some places that we've had success applying edge computing. This, of course, isn't the only places we could do this, but this is where we've tried and where we've had success and where we're currently actively working in. The first one here, kind of in the middle on the right, is the artificial lift. We have several applications to optimize artificial lift. I've mentioned gas lift applications. We have an analytic that can optimize the amount of the pressure into the well to produce the most fluids out of the well. We have another application that I'm going to go in a little bit of detail about intermittent shut-in wells. So the well's depleted and you're using intermittent shut-in to get more gas out of the well. We have an analytic to help with that. The reciprocating compressors up here up top. We have use cases where we attach an edge computer to a reciprocating compressor. We gather data from sensors that have to be there per API standards, and we use that data to predict failures and to suggest changes to improve the efficiency of those reciprocating compressors. Tank level monitor is another analytic we've worked on. We needed a flow meter for our gas lift application. They didn't have a flow meter on site, so we took the tank levels and we ran some math, turned those tank levels into a sort of virtual flow meter. So that's a good example of how this can be used, of the power of taking your existing equipment and augmenting it with an edge computer. And then the last one over here to the right is measuring combustion efficiency. We're working on an analytic for that. So the point of this is to automate and oversee different aspects of your well pad remotely. So someone specifically mentioned, rather than having to fight every single individual fire, if you've got some of these applications that can be handled by a computer on a day-to-day basis, it allows your production engineers to spend their time on more important or more drastic cases. So the reciprocating compressor, just to show some data of how this has worked in real life. This chart here shows data that we gathered from a reciprocating compressor in a gas gathering application. This was in the Permian Basin. We've got two lines here. We've got an orange line and a green line. They both represent the discharge pressure of this two-cylinder reciprocating compressor. So the orange line is cylinder 1, the green line is cylinder 2. As you can see right here, I'm gonna get a little laser pointer for just a second. Right here, there is a spike in the temperature, and that correlates. At the same time, there was an alarm from the SCADA system saying, hey, something's wrong with your compressor. Same thing happens here on the green line. There's a spike and the SCADA system says, hey, there's a problem with your compressor. We were plugged into this device using our analytic on the edge device, using our application on the edge device. It triggered a warning about 80 days before each of these failures. That gave our customer 80 days to go figure out what exactly is wrong, fix that issue before it becomes a full-on failure. And so that the impact of this particular case was about 47 MMCF, a total loss of revenue of about $73,000 and about $1,000 of fuel recovery costs. So you can clearly see how nice that is for a customer to be able to see these in advance and be able to plan for these things. Another application, I mentioned this briefly. This is an application in a depleted well. They're gathering gas out of the well. What they do is they shut in the well in order to build pressure, and then they open the well to get gas out of it once the pressure's been built up. Those are two different variables that the customer has to figure out. What pressure do I shut in my well? What pressure do I open it back up to get the most gas out of the well? We developed, in partnership with this customer, we developed an analytic that would suggest to their controller, it would suggest to shut in at pressure at a certain pressure and open at another pressure, and then it would measure the result. Using a clever trick with those suggested pressures, it could quickly generate a curve and produce the optimal shut-in pressure and reopening pressure. That's kind of what this graph on the right here is showing. So on the left is the result. The gray line represents how this particular well was performing, their cumulative gas before this analytic was installed. The blue dotted line represents, had they continued along that line, this is how much production they could have expected. That means they're getting the same production and the well is not the weld decline is not affecting their production. The blue line is what we were actually able to get out of the solid blue line. So as you can see, there was improvement here. As the analytic tested different shut-in pressures and opening pressures, it was able to produce more and more gas. Eventually, up here, it had found a really good point to stay at, and it can stay at that point and track it over time. So this is one example. We've tested this on about 10 different wells. We've had an average improvement of 7% production, and we had a huge side benefit that neither us nor the customer expected. If you don't control the pressures carefully, you can have fluid buildup in the column, and that prevents gas from getting out, and you have to send a technician to manually unload the column. That not only involves time for the technician, it also involves venting a lot of emissions and wasted production, which is both very bad things. As this analytic was installed, we noticed they were having to do this a lot less. As a matter of fact, it reduced it from 38.5 visits per month on average to 1.3 visits per month. That's a huge side benefit that we didn't even necessarily plan for. We were aiming for better production, and we got this. Another important aspect of this is automated optimization. So you've got that computer watching that well 24 hours a day, 7 days a week. It's like having a production engineer watch it all the time. No production engineer has that amount of time, and they're all managing a whole bunch of different wells. So it's pretty incredible that this algorithm is able to do that on some of these shut-in wells. The last use case that I'm going to talk about is it's a product that we sell. Panametrics here is a product company, a Baker Hughes business that sells a flare meter and a flare controller in downstream environments. This is a proven algorithm that works in downstream environments. With this edge computing, we saw an opportunity to try to bring the intelligence that exists in this Flare IQ product to an upstream environment, which is very different. We're no longer in a factory. We no longer have reliable communication and infrastructure. We're now out in the field with a lot of those, givens that would happen in a downstream environment. A lot of those sensors and infrastructure and SCADA system probably don't exist. So we're taking this proven analytic that can measure the efficiency of a flare, and we're attempting to bring this to the upstream market. So what this would entail basically is connecting our industrialized computer to a PLC or a flare meter in the field via Modbus. We would need some sort of flow meter to the flare. On that computer, we can calculate the net heating value and the combustion efficiency of the flare, and we can send that data to wherever a customer wants to view it, whether that's a remote database in the cloud, whether they just want to go to the site and see it on the local edge device. We can do any of those things. The point of this is to increase transparency and accuracy. It allows for continuous online monitoring. It's a simple installation that can operate with existing SCADA infrastructure or sensors. It allows you, importantly, to replace emission factors with real-time combustion efficiency percentages and total hydrocarbon destruction efficiency. As I mentioned, we're trying to bring this to the upstream market, and we are looking for people who are willing to partner with us on this. The hope being that we can demonstrate that your flare is more efficient than than our emission factors are assuming they are, allowing you to produce more. Also, with the stringent regulations around emissions and the ever-changing nature of those regulations, it's always better to be out ahead of this and have good measurements on this. So if you are interested in partnering on this with us, please reach out to me. I think my email will be available. If not, Brooke Simmons and David will know how to get a hold of us, and we can go into further detail about how this would work. That being said, any other questions about edge computing in general or any of the use cases we've discussed?
Hey, Sam, let's can we go through your three case studies here, and I'm just going to give you a few comments if you don't mind.
Absolutely.
Go back 2 slides, and
Yes.
I could tell you some real life things that okay, for example, the data that you're picking up off the computer. This is a really good. This has been going on for a while. Being able to use this kind of information real time is the new. One of the things that is a very good corollary to what you're measuring here is when the compressor goes down on low flow, what that will indicate is there's a problem, and it's not always a single well as you did in your diagram. It may be a series of wells, and this is a central delivery point compressor. That's more often the case, and they're bigger compressors, so they have more tech. So when you go down on low flow here, it is indicative of a problem with a well, a delivery problem. And that data is extremely valuable to operating by exception. So we would send our lease operators out immediately to that particular site, to the wells behind that compressor, instead of going, doing a route. So that is a corollary to what you have here that would be very, very valuable to our constituents. The next
David,
slide. Go ahead, Sam.
Excuse me, that root cause analysis that reveals is monumentally important, as you probably recognize, because historically when a compressor goes down, then the compressor operator blames the oil field operator, and the oil field operator blames the pipeline company, and everybody's blaming one another because there isn't a clear indication of what actually was the cause versus the effect. So that is a sidebar to that, of monumental value.
Yeah, you're also measuring discharge pressure. So when your line pressure goes up, who's responsible, right? So this actually has a lot more applications than even the one that you sent, and you guys have probably already thought about this, but that's one that would help our constituents. In the second case study, the loading up of the wells, changing travel times of plunger lift wells is the next corollary for this. So how much time, as you're changing, this is a real simple setup with an intermitter controller that's based upon pressure. So you go as your pressure goes down, you shut the well in to build back up and unload the well. And so you're still having, in your example, it's significantly reduced the amount of time that you have to go out and swab the well back in, is what they're doing here. But these things graduate to plunger lifts, because the plunger lift will move the fluid, and it's operated under the same principles with the low pressure, high pressure. So there's another corollary here as well that would be important to our guys. The third one, the third example that you had, this is very interesting, but this actually is a little bit of a Pandora's box for us. The measure that the high, we all are trying to cut down flaring and carbon release, right? That's a goal of almost everybody that's stated. It's an ESG goal. It's a measurement. This actually helps reporting, but it also creates a couple of things. One is the potential for that the actual information of flared hydrocarbons could bring up a royalty question. So you know the inefficiency of your system. Now you got to pay royalty on what you flared, or something. And and people are trying. This is especially a problematic for smaller operators. So keep that in mind. That causes that issue as well. We want to hit our ESG goals. Everybody does, but we don't want to expose ourselves to a bunch of potential lawsuits or additional costs. So the goal here was to get somebody to partner on this. Is what do we do with that flared, and can we measure it to a point where is there an application for generating electricity or for anything with that hydrocarbon? So the next vertical that you got to find is, what do we do with our flare gas when this happens, and is there enough of it to warrant that kind of capital investment? So that's what the Panametrics is definitely this tech business that you guys have created is definitely going to help with our ESG reporting, and it's going to make people not want to, less flaring, right? But we're going to have to have a little bit of well, what do we do if we can't? No matter what we do, we have X amount of downtime and we're flaring. So what do we do with that? And there's a bunch of super cool ideas. I read an article actually a couple of days ago where they were generating electricity with flare volume, and it was being used from a crypto standpoint of putting powering a cryptocurrency thing, which was kind of interesting, made it even more. But anything that any electricity generation that we can have out there, we can find a place to use it. But that's the vertical for this one that needs to happen.
Well, to all our panelists here, this has been a great discussion. We have just sort of scratched the surface when it comes to the digital oil field and the technological revolution that's underway. I know Maki and her team are always available for follow-up questions. Mr. Chairman, did you have anything else to add?
Well, we certainly appreciate this, and it's just such a great thing for us because they're right here, and of course, we're very happy with the collaboration. I saw an OU collaboration, and I saw, of course, the big one with OSU. It's excellent. So we certainly appreciate, the leadership that Baker Hughes has shown there. Thank you.
Thanks a lot, and really appreciate all the feedback because there are things that we've been looking at, but we need the customers to really validate it and help us test. So I think that's definitely something we're looking out for. And always great to have discussion with these types of platforms for broader operator discussion.
Where can we lay our hands on here's our current projects, and here's like Sam Tanner said, hey, this is one we need some help with financing. Is anybody interested? Where do we lay our hands on that information? Is that a website thing, or can we get that for our folks, or how would we do that?
Yeah, we can definitely send material that we have in terms of our consolidated portfolio, any help we need. And also we have a few things on website, so I can coordinate with Brooke and Cody offline to provide those links and material. And if there's follow-up discussions to have, happy to do that as well.
Yeah, Maki, let's coordinate on that, and we'll make certain as this thing sort of lives on for a while that folks have an opportunity to track that information down.
Yeah, no, perfect. And if there's specific themes that the audience is interested, we can really cater that for the next session, for example, right, if it's a few months' time or so.
Lots of good stuff talked about today. We're just scratching the surface. I really want to have this practical conversation about where this all is going and how do we get our heads around the over-the-horizon vision of the digital oil field, and how we also transition that technology from larger companies and sort of the RT-DNA phase all the way down to the guys in the field and the family-owned business, and how they think about that too, how we get that, what the affordability is. Those kind of questions are going to be important drivers for the next phase of the conversation. So, yeah, guys, I really
just as a information, what Sam has shown in terms of example, those are mainly with very small operators. So it's not really working with the big companies. It's really finding the need within any types of customers really. And for us, it has been actually more the small companies. Because some of the larger ones, they're doing it themselves internally in-house. So, different dynamics, definitely.
Great. Anything that benefits our constituents. And if one of us has that particular issue, a bunch of us have. So it's valuable to us. Thank you so much.
Thank you. Let me hit the highlights of what's coming up next on the Morning Fuel agenda. So we got March 31st with Senator James Lankford. You guys will want to tune into that. He has some great information to share. And also it's important to remember that Senator Lankford now is on both Energy and Natural Resources and the Finance Committee and Homeland Security and Governmental Oversight, as well as Indian Affairs. So this is going to be an important one for everyone to tune in on next week, March 31st. After that, Lieutenant Governor Matt Pinnell is going to be joining us. What a great advocate for the state he is and for our industry. And then just want to remind everyone that we have an updated events calendar. April 26th, the Alliance Open Golf Tournament, a great opportunity for us to get back together here as we warm up and start doing some business together. So thank you very much to all our participants today. Mr. Chairman, do you have anything else to add?
That's it, guys. Thank you again.
Great. Thanks, team. Appreciate you.